Himalayan Gazetteer by Edwin T. Atkinson. Chapter 2: Physical Geography of the Himalaya. Contents: the Himalayan river basins, the Indus Basin, subordinate systems of the Indus Basin, the Ganges Basin, subordinate systems of the Ganges Basin, the Brahmaputra Basin, subordinate systems of the Brahmaputra Basin, systems of Tibet, Labnar Basin, Oxus Basin, plains of Hindustan, Indus Plain, Indian Desert, Gangetic Plain, Assam Valley, Bhabar, Tarai, Sivaliks, dunes, extent of Bhabar, cause of the deposit, Hodgson's oceanic theory, fluviatile theory, Tarai, Sivaliks, dunes, Ganges to Brahmaputra, Lower Himalaya, materials of the mountains, Eocene period, mode of mountain formation, mountain sculpture, ice wedges, avalanches, glaciers, rain, rivers. The Himalaya. We have already decided to restrict our use of the word Himalaya to that portion of the great mountain girdle which lies between the bend of the Indus on the west and the unexplored gorge of the Brahmaputra on the east. Hodgson in 1849 estimated the length of this range at 1,800 miles with a mean breadth of about 90 miles, a maximum breadth of 110 miles, and a minimum breadth of about 70 miles. In fixing the breadth of the Himalaya, however, as in determining its length, we have similar difficulties to contend with. For, as we have seen that the popular estimate as to the boundaries of the range may possibly be correctly extended both on the east and on the west, so on the north, the channels of the Indus and the Brahmaputra, which are commonly assigned as the northern limit, are found in a plateau but little lower than the passes by which the traveler crosses the first line of snowy mountains into Tibet. On the south, we have a well-marked descent into the plains of India, but on the north, there is no immediate descent to a lower country beyond. On the contrary, range after range is met with to the north, many of which may compete in altitude with the snowy mountains seen from the plains of North India. River basins. Before proceeding to a closer examination of the form of that portion of the Himalaya lying within the province of Kumaon, it will be convenient briefly to describe the river basins throughout the Himalaya and endeavor to trace the general law underlying their arrangement. For, as this depends in the main on the direction of the great ranges and the position of the great peaks, a consideration of it will conduce to a clearer apprehension of the entire mountain system itself as well as of the relations of its various parts. We find that from a water parting about longitude 81 degrees east and almost immediately due north of Kumaon, the drainage of the southern part of the Tibetan plateau flows northwest in the Indus and southeast in the Brahmaputra. These two rivers maintain a course along the length of the tableland and receive as they proceed the drainage of a large part of its breadth. The exceptions being, first, the eastern border, which apparently is drained by the Lutse, the Lansang, and the Muri Usu, one of the sources of the Yangtze Kiang. Second, an occasional strip along the southern edge from which the water passes off more or less directly to the south through the Himalaya. And third, the northwestern part from which the water has no escape but is collected in lakes at the lowest level it can reach. The waters thus accumulated in the two great streams are at length discharged by two openings in the Himalayan slope through the plains of India into the Indian Ocean. No great portion of the drainage of the tableland, so far as we know, passes in the opposite direction through the northern slope, and the area that discharges itself southward at points intermediate between the debouches of the Indus and the Brahmaputra is, with one exception, that of the Sutlej, comparatively small. The waters of the northern slope, with a small area of the tableland adjoining, flow down to the plains of eastern Turkestan, while, in like manner, those of the southern slope, with the drainage of the exceptional area along the southern border of the tableland, which passes through the line of water parting from the north, give rise to such rivers as the Jhelum, Chenab, Ravi, Jamna, Ganges, Kali, Gandak, Kosi, and Teesta. We thus see that the northern crest of the tableland, or the summit of its northern slope, practically forms the water parting between the rivers that flow southwards and those that lose themselves in the plain of Gobi. In the southern crest, we have a subordinate water parting separating the rivers that fall into the Indian Ocean into two classes. First, those that rise on that slope and flow directly down it to the plains of Hindustan, and secondly, those that are collected along the tableland and are finally discharged also through the southern slope, chiefly by two concentrated channels at distant points towards the ends of the range. Captain Henry Strachey has called the northern crest of the tableland the Turkish and the southern the Indian water parting. Indus Basin. If we examine the river systems having their source in the Himalaya, we find a regularity of plan and arrangement which at first sight would not be expected. Taking the Indus Basin and its system, we see that the Sutlej and all the rivers that join the Indus on its left bank have a southwesterly direction towards the Arabian Sea. On the east, this system is bounded by the small inland basin of the Kaggar, which receives the drainage from an inconsiderable portion of the outer hills between the Sutlej and the Jamna, and finally loses its waters in the Indian desert. The eastern water parting of the Indus system is found in the elevated range extending from the main Himalayan mass along the left bank of the Sutlej to Rupar, and is continued thence in the uplands bordering the Khadir of that river until it meets the Arvali or Aravalli range, which constitutes the northwestern abutment of the tableland of central India. The character of the slope towards the southwest will be best understood from the following table of heights taken along the course of the Sutlej to Ludhiana and thence by the Grand Trunk Road to the Jamna. Taru, about 2 miles below the junction of the Panjnad and Indus, 337 feet above the level of the sea. Bahawalpur, 375 feet. Noor Shah, 481 feet. Pir Khalis, 7 miles northeast of Bahawalgarh, 548 feet. Fazilka, 588 feet. Firozpur Cantonment, 645 feet. Jagraon, 765 feet. Ludhiana, 806 feet. Ambala Church, 899 feet. And Madalpur on the banks of the Jamna Khadir, 906 feet. From Sodiwala in the Firozpur district, southwards on the 75th meridian, we have Sodiwala, 718 feet. Ahmadwala, 705 feet. Sirsa on a mound, 737 feet. Level of Sambar Lake 1184 feet. These observations show a slight depression towards the south in addition to that towards the southwest and would make us include the Kaggar inland basin in the Indus system. The Sotra or Hakra, the ancient river of the Indian desert, seems, however, to have once had its debauch in the Rann of Kutch and would therefore be still entitled to be considered separate. To the west, the Ravi and the Chenab run in lines almost parallel to the Sutlej as well as the Jhelum from the town of that name until it takes a bend to the south to its junction with the Chenab. To the west, the water parting of the Indus commences at Cape Monze on the Arabian Sea and advances nearly northwards along the Hala Mountains to the east of Sohrab, Kalat, and Quetta or Quetta. It thence continues in the same direction along the western Sulaiman Range, also known as the Konak and Khub Jadran Range, to the Safed Ko at the head of the Kurram Valley. Thence it follows the crest of the Safed Ko westwards to the hills north of Ghazni, where it separates the southern affluents of the Kabul River from the waters of the small inland basin of Lake Abistada. The direction is then continued northwesterly to the ridge separating the headwaters of the Argand Ab from those of the Kabul River, and again in the range that separates the waters of the Halmand Basin from the most westerly affluents of the Kabul River, whence a transverse ridge near the pass to Bamiyan connects the line of water parting with the Hindu Kush. For 300 miles, the line follows the Hindu Kush to its junction with the great Tagdambash Pamir near the Barogil Pass. It then follows the Mustag Range but cuts through it around by the Karakoram Pass to the north so as to include the tributaries of the Shyok and proceeds in a southeasterly direction by the Aling Gangri to its junction with the Gangri at Kailas, where a transverse ridge separates the headwaters of the Indus, the Brahmaputra, and the trans-Himalayan feeder of the Ganges system. The Indus has a length of 1,800 miles, and according to Mr. Saunders, its basin has an area of 3,72,000 square miles. Subordinate systems of the Indus Basin. The Hala Mountains to the south of the Mula Pass are better known as the Kirdar Hills and as the Poob Hills, and the drainage from them loses itself in the plains before it can reach the Indus. The same may be said of the drainage through the Mula and Bolan passes and that by the Thal Valley. To the north, the Luni, Gomal, Kurram, and Kabul rivers, each possessing a perennial stream, have an easterly course more or less parallel to each other and break through the range bordering the right bank of the Indus by deep and narrow gorges which form the passes into the upper country. The Kabul River itself is the drainage channel for the very elevated country from the hills north of Ghazni to the Barogil Pass north of Chitral and from Naushera to the pass leading to Bamiyan, and thus forms a compact subordinate system well deserving of separate study. The upper waters of the Jhelum drain the Tile and Kashmir valleys and have a general direction between west and north to Muzaffarabad, where they unite and meeting a meridional ridge take a bend southwards to the plains. The Chenab, in the upper portion of its course, known as the Chandra, has a similar direction between west and north until it meets the spurs from the range which forms the water parting between it and the Jhelum, whence it seeks an outlet southwards towards the plains. The Ravi runs in a valley parallel to that of the Chenab and south of it until it meets the outliers of the range that forms the water parting between it and the Chenab, when it also turns suddenly southwards towards the plains. Next comes the Bias, which has also a westerly direction until it meets the ridge between it and the Ravi, when it takes a bend to the south through the outer hills. The upper course of the Sutlej has a similar westerly trend until it meets the great obstruction culminating in the Leoporgul Peak, after which the direction is between west and south until it enters the plains. A range runs between the Sutlej and the southern branch of the Indus from the meridian of Tirthapuri by Gar to where it is joined by the ridge connecting it with Leoporgul, and thence into Rupshu to the north of the Tsomoriri lake, and constitutes the subordinate water parting between the Sutlej itself and the Indus. Thus, we see that the great feeders of the Indus system from the west have a similar character, and that those from the east, from the Himalaya proper, have a general westerly direction in the upper portion of their courses in the hills until they turn southwards towards the plains, where the direction is southwest to their junction with the Indus. The Ganges Basin. Next, we have the Ganges Basin with its subordinate systems. To the north, the water parting, as a rule, follows the Ghat line of the Himalaya, and on the extreme west separates the sources of the Jhat Ganga, one of the headwaters of the Bhagirathi, from the Hope Gad, an affluent of the Sutlej. North of Kumaon, however, we have a phenomenon similar to that observed near the Karakoram Pass, where the waters of the Shayok, Yarkand, and Karakash rivers have a common origin in that elevated plateau at no great distance from each other. We find that to the east of the Untadhura Pass, north of Milam in Kuaon, the water parting of the Ganges Basin crosses to the north of the Ghat line to a place called Tara, where the sources of the Sutlej and the Karnali lie close together, divided by an almost level plain across which a man might walk from one river to the other in an hour or two without a vertical ascent or descent of 500 feet. Yet the waters of one stream seek the sea at Karachi and of the other by Goalundo. Further east, the water parting is continued in the Ghat line to the Arun River, which has its sources to the north and forces for itself a way through the Himalaya to the plains. The water parting then follows the eastern boundary of Nepal to the plains, where an intricate system of drainage is met with, throwing off feeders sometimes to the Brahmaputra and sometimes to the Ganges down to their junction at Goalundo. Following the line on the west from east longitude 79 degrees and 11 minutes and north latitude 25 degrees, we find in the extreme northwest that the water parting keeps to the crest of the range running along the left bank of the Baspa, an affluent of the Sutlej, and is continued by Hattu to the ridge on which Simla is built. Thence it proceeds southward and then eastward along the right bank of the Giri to the junction of that stream with the Jamna near Rajghat. Here the water parting turns southwards along the line separating the drainage area of the Kaggar system from that of the Jamna, and continuing along the Aravalli range and the edge of the Malwa plateau passes through the Jabalpur and Mandla districts, separating the sources of the Narbada from those of the Son, and then along the range connecting the Satpuras with the Rajmahal hills to the plains, where it follows a course along the left bank of the Sabanreka to the sea. Mr. Saunders has given the length of the main stream of the Ganges as 1,514 miles and the area of its basin at 391,000 square miles. Subordinate systems of the Ganges Basin. The Ganges Basin, like that of the Indus, possesses several subordinate systems that may be called in their order from west to east the Jamna Ganges, Karnali, Gandak, and Kosi systems. The alpine basin of the Jamna Ganges system is bounded on the west by the well defined range which descends from the Jamnotri group of peaks to the Sutlej River, and on the east by a similar ridge descending from the Nanda Devi group of peaks and separating the waters of the Pindar from those of the Himalayan Sarju. To the north, the Ghat line separates it from the source of the Karnali on the east and the source of the Sutlej on the west. Although the upper waters of both the Jamna and the Alaknanda, or principal source of the Ganges, have at first a westerly direction, they soon take a bend to the south and form the main channels to which are directed their affluents from either side. It is remarkable that, with the exception of the Ram Ganga, which unites with the Ganges in the Farrukhabad district, neither the Jamna nor the Ganges before their junction receives any considerable affluent of Himalayan origin during its course through the plains. The western boundary of the alpine basin of the Karnali is marked by the ridge extending from the Nanda Devi group between the Pindar and Sarju rivers already noticed. The eastern boundary is formed by a similar ridge descending from the Dhaulagiri group of peaks. To the west, the Sarju, eastern Ramganga, Gori, and Kali enter the plains in one stream as the Sarda. Then the Svetaganga Karnali and Bheri form the Karnali, and further east we have the Jingrak or Rapti and its affluents. All unite in the plains to form the Gogra, which joins the Ganges to the south of the Ghazipur district. But this unitizing law is better exemplified in the alpine basin of the Gandak, which reaches from the Dhaulagiri group to the Gosain Than group of peaks. We have here 7 rivers named in order from west to east: the Barigar, Narayani, Sveti Gandaki, Mashyangdi, Dharamdi, Burhiya Gandaki, and Trishul Gandaki. These are called the 7 Gandaki by the Nepalis and unite their waters at Tribeni within the hills to form the Gandak River of the plains. Here we have what Hodgson terms an admirably defined natural division lying between two great groups of peaks. In the same manner as the Karnali basin is bounded on the west by the spur descending from the Nanda Devi group of peaks and on the east by the ridge from the Dhaulagiri group, so the Barigar of the Gandak system does not receive a single streamlet from the westward of the Dhaulagiri ridge, nor does the Trishul of the same system receive any water from the east of the ridge descending from Gosain Than. The alpine basin of the Kosi lies between the Gosain Than group and the Kanchenjunga group of peaks, and like the Gandak system, consists of 7 rivers known as the 7 Kosis. These, named in their order from west to east, are the Milamchi or Indravati, the Bhotia Kasi, Tamba Kosi, Likhu Kosi, Dudh Kosi, Arun, and Tamra or Tamor. The Arun has one of its sources to the north of the line of snowy peaks seen from the plains, and the Tamor is also said to have trans-Nivian affluents, but all the others rise on the southern slope of the Himalaya and unite within the hills at Varaha Kshetra above Nagpur. The subordinate systems of the Ganges basin thus appear to be strongly characterized by a common origin within an area bounded on the north by the Ghat line and on the west and east by well-marked groups of culminating peaks, whence ridges descend and form the water parting between successive systems. Brahmaputra Basin. The Brahmaputra Basin in its full extent has not been explored, but sufficient evidence has been collected by recent travelers to show that from the water parting between the sources of the Brahmaputra and the Indus, the northern water parting of the former river continues in a range of lofty peaks on its left bank to the bend towards the south, by which it reaches the plains of India. This range has a direction southeast and to the west of the 86th meridian is sufficiently distant from the Brahmaputra to allow of such affluents as the Chachu and the Charta rivers. About the 86th meridian, a line of peaks culminating in the Thargotla stretch in a northeasterly direction to the Gyakarma group of peaks southeast of the Karing Cho or Karing Lake, one of the sources of the Nakchu Ka. The drainage of the southern slope of the range is sent by the Dumfu Chu into the Karing Lake, so that the northern water parting of the Brahmaputra must here approach much closer to the river and run in a southeasterly direction. On the 89th meridian, it descends as low as the 30th parallel in the Siang Lahu range, which appears to be connected with the great Ninjin Tangla range of snowy peaks to the south of the Jang Namcho or Tengrinor Lake, with a trend to the northeast, for it gives the headwaters of the Kichu or Lhasa River from its southern slope, as well as other important streams further east, regarding which our information is still very imperfect. To the northeast, we find the Nakchuka or Hota Sanpo, a large river that issues from the Chargut Lake about north latitude 32 degrees and east longitude 89 degrees and flows eastward, having its drainage area on the south bounded by the water parting between it and the Brahmaputra basin. This great river takes a bend to the south and, according to one of the Pandit explorers, flows by Tsiamdo on the road from Lhasa to Bathang and thence through Amdo to China under the names Machu and Kong Kong. These names would connect it with Yangtze, but if it flows by Tsiamdo, it should be one of the branches of the Lansang, the name of the upper portion of the Mekong or Cambodia River. Des Godins notes that the Nutse or Lutse is known as the Ngenkyo in Tibet, a name which may perhaps be referred to the Nakchu, and it would then be the headwaters of the Salween, whilst others claim it as the source of the Irrawaddy. All that can therefore be said is that there is a great river in eastern Tibet, between which and the Brahmaputra is an unexplored tract of country, and within it will be found the eastern water parting of the Brahmaputra. So far as we may conjecture from the imperfect materials at our command, and the range that forms the northern water parting of the Brahmaputra takes a sudden bend towards southwards between the 96th and 97th meridians along the right bank of the Lutse. Thence, one branch proceeds westwards in the Patkoi range and another southwards between the Irrawaddy and Salween. To the south, the water parting follows the crest of the Patkoi range and is continued westwards in the Manipur, Lushai and Chittagong hills, where it separates the southern affluents of the Brahmaputra from those of the Burmese systems. To the west, the water parting is conterminous with that of the Ganges basin. Mr. Sanders estimates the course of the Brahmaputra at 1,800 miles and the area of its basin at 361,000 square miles. Subordinate systems of the Brahmaputra basin. Following the systems that carry off the drainage from the southern slopes of the Himalaya and join the Brahmaputra in its course through the plains, we trace much the same regularity found in the subordinate systems of the Ganges basin further west. The Teesta system of Sikkim is bounded on the west by a ridge descending from the Kanchenjunga group of peaks, and on the east by a similar ridge from the Chumalari group that also forms the eastern boundary of Sikkim. The alpine rivers of this system in order from west to east are the Bari Ranjit, Ratong, Lachen, Lachung and Rangchu, and all unite within the hills above Kalimpong to the east of Darjeeling. The alpine basin of the Tarsa Gangadhar system extends from the Chumalari group on the west to the ridge descending some 15 miles east of the 90th meridian in the 28th parallel, and which separates the waters of the affluents of the Tarsa from those of the Manas system. The rivers of this alpine basin from west to east are the Ammo, Dor, Par, Wang, Ma, Pachu, and Tanchu, which unite within the hills to form the Tarsa and the Gangadhar tributaries of the Brahmaputra. Further east comes the Manas system, of which the western water parting is conterminous with that of the Tarsa Gangadhar system. On the east, it is bounded by a ridge descending from the group of snowy peaks to the west of the Karkang Pass, crossed by the Pandit on the Tawang route in 1873, and for its alpine feeders has the Mati, Manas, Kuru, Lopra, and Tawang streams, which apparently also unite within the verge of the mountains to form the Manas. Eastwards lies the Subansiri system between the Manas and the Dihong. The Sikangchu, which rises to the south of the Karkang Pass, probably forms one of its sources, but the remainder lie within the wild country of the Abars and have not yet been explored. The southern affluents of the Brahmaputra during its course through the valley of Assam are not so important and may be divided into two classes: those which carry the drainage of the northern slope of the hills inhabited by the Singpho, Aror, and Naga tribes and fall directly into the Brahmaputra, and those which carry the drainage of the northern slope of the hills of the Lushai country and Hill Tripura and of the southern slopes of the Jaintia, Kasia, and Garo hills to the Meghna, which joins the Brahmaputra below Dhaka. To the former class belong the Dihing, Disung, Southern Dhansiri, and Kopili, and to the latter the Barak, Surma, and Dhani. To the extreme east of the Assam Valley is a snowy range from which issues the Lohit or Brahmakund river that gives its name to the Brahmaputra. But geographers have applied the same name to the great river flowing by Lhasa and which the best authorities identify with the Dihong that joins the Lohit in the upper valley of Assam. The, the more general name of the Brahmaputra in the upper portion of its course seems to be Sanpo or Sanpo, meaning the river or the great river, used like Ganga in the plains and Kiang in China. In Assam, the name varies with the tribe inhabiting its banks or those of its tributaries, so that the designation Brahmaputra to express the entire course of the river from its source to the north of Kumaon to its junction with the Ganges must be considered a convenient device of geographers and not a term based on received usage. We have seen that at its junction with the Lohit, the Brahmaputra is called the Dihong. East of this junction, the Lohit receives a tributary from the north called the Dibong, and on the south, another called the Dihing, and again one called the Disung. Much confusion has resulted in Assam geography from not remembering that all these names refer to different rivers. Tibet. We have already noticed the division of Tibet into the eastern, western, and central provinces. It is called Sitsang by the Chinese and is also known under the names Tupu and Mutu or Upper and Lower Tibet. From the accounts of the eastern province in the writings of Klaproth, Hook, Blakeston, Cooper, Des Godins, and Gill, we may assume that the drainage to the east of the 96th meridian has a southerly direction and that the general conditions resemble much those further west. Pengshan on the Yangtze in western Sichuan is 1,500 feet above the level of the sea. At Qingtu, some 70 miles due north of Pengshan, Cooper in March found the fields in the neighborhood occupied by luxuriant crops of wheat, barley, sugarcane, and opium, the latter of which demands a climate similar to that of the plains below the Kumaon Himalaya. The same traveler crossed the Yalung and Kinsha branches of the Yangtze between Qingtu and Bathang, and beyond Tatsienlu entered eastern Tibet, where yaks are used in the carrying trade and a more alpine climate is met with. Bathang on the west has much the same position with respect to the elevated highland to the north that Qingtu has on the east, but lies a degree of latitude more to the south than Qingtu, so that from the meridian of Batang, the range dividing the Tibetan plateau from the plains of China seems to take a northeasterly direction. The feeders of the Yangtze and other rivers find their way through this range by a series of gorges similar to that of the Dibang further west. Between the Yangtze and the Dihang, we have two great rivers, the Lansang identified with the Mekong or river of Cambodia and the Lutse or upper course of the Salween. Father Des Godins informs us that the Mekong has its origin in about 33 degrees to 34 degrees north latitude in the mountains south of Kokonor, and the Lutse further west is known as the Ngayen Kyo in Tibet. But whether this name is to be regarded as one with the Nak Chu Ka of the Pandit explorer is left to future travelers to decide. Turning now to the upper portions of central and western Tibet, we find from the Pandit explorations that the drainage to the north of the northern water parting of the upper portions of both the Indus and the Brahmaputra flows into a number of lakes. East of the 84th meridian, these lakes appear to be connected the one with the other and eventually with the great river Nak Chu Ka, which has an easterly direction in the upper part of its course and finds a southern outlet in one of the great rivers to the east of the Dihong. From the Pangong Lake on the west to the Longkor Cho between the 83rd and 84th meridians on the east, the drainage is collected in a series of depressions without any outlet, each of which is the center of a subordinate minor system of its own. We do not know of any considerable stream proceeding northwards or westwards from this tract. This lake system is a characteristic feature of the orography of northwestern Tibet. The waters of these lakes are generally brackish and the margins exhibit expanses of salt marsh. Streams of fresh water are found, but in their course towards the lakes, these rapidly become brackish and in the end, little influence the quality of the lake water itself. According to the Pandit, the country to the north of Garge and Garchetol is a great uninhabited plain. It was formerly customary to travel in a north-northwesterly direction from Thok, Daurakpa for some 20 days to the range overlooking the Gobi plain in which the commercial entrepot Nari Tharu lay. A 2 month journey from Thok Daurakpa to the northeast brought the traveler to Ajan, also a commercial center. This road lay throughout over an extensive plain. No large mountains were seen and no streams were crossed. Drinking water was obtained from a number of freshwater lakes, mostly dependent on the rainfall for their supply. From these reports, we learn that northern Tibet is a plateau of great elevation without inhabitants and possessed of few streams. As we approach the west, the boundary ranges that support the Tibetan plateau between them on the north and south gradually incline towards each other so that westwards of the Pangong Lake they are little more than 50 miles apart. Here we find the water parting of the Indus and Lobnar systems in the elevated Dipsang plain, which attains a height of 18,000 feet above the level of the sea near the Karakoram Pass, which is at a height of 18,550 feet. From the Karakoram Pass on the north flows a feeder of the Yarkand River, and from the east an affluent of the Karakash River, both of which belong to the Lobnar system. On the southeast, only 11 miles from the pass, the Daulat Beguldi encamping ground is close to one of the feeders of the Nubra branch of the Shayok River that belongs to the Indus system. In one case, the waters lose themselves in the Gobi Desert, and in the other, they reach the Indian Ocean at Karachi. If the statements of Kostenko and Savetsov be accepted, we have here in the West an analog of the arrangement that has been described as characteristic of all the river systems along the southern face of the Himalaya between the Jamna and the Brahmaputra. The alpine basin of the Yamanyar lies between two great groups of peaks some 30 miles apart. On the southeast of the Yamanyar is the Thagarma group, of which the Mustag Ata peak attains an elevation of 25,350 feet above the level of the sea. On the northwest, there is a similar group, of which the Tash Balik peak reaches an elevation of 22,500 feet. The Yamanyar collects its waters in an elevated valley between these groups and the water parting range on the west, which is known variously as the Thagarma Plain or Plain of the Kichik Karakul. The groups themselves are in advance of the water parting range and are connected with it by transverse ridges. That on the south connects the Mustag Ata group near the Kok Mainak Pass with the water parting range west of the Nezatash Pass, while that on the north has not yet been accurately defined. Spurs from the groups descend northwards towards the plains and effectually divide the waters of the Yamnyar from those of the Kashgar Darya on the west and from those of the Yarkand River on the east. It has generally been supposed that these two groups of peaks belonged to a great meridional range, but Severtsov, who has had recently exceptional means for obtaining an accurate estimate of its character, distinctly states that these two peaks were supposed to be connected by a continuous range, while the real fact is that each is respectively the highest point of separate small, high mountain knots capped with eternal snow. We have, therefore, in the west also an apparent snowy chain of mountains as seen from the plains, but which on closer examination resolves itself into groups of snowy peaks in advance of the water parting range from which they are divided by an elevated valley. This valley gives rise to a river that makes a way for itself between the boundary groups to the plains below, while the groups themselves are connected by transverse ridges with the line of water parting. A ridge from Mustag Ata to Yangit Hisar separates the drainage of the northern slope from that of the Kinkol River on the east, and a second ridge follows at some distance the left bank of the Yamanyar, which shortly after its issue from the mountains is absorbed in artificial branches or canals for irrigation purposes. The whole system is a remarkable illustration of Hodgson's formula for the river systems of the eastern Himalaya. Oxus Basin. The alpine affluents of the Yarkand River, known as the Sarikol and Zarafshan rivers, also illustrate the unitizing principle observed elsewhere. They are separated from each other by the Kandar range, which descends in a northeasterly direction from the water parting range to the south and terminates where the Sarikol and Zarafshan unite their waters within the outer range of hills to the north. The Oxus system further gives an example of another of the characteristic features of the Himalayan river systems. The water parting follows the line of the Hindu Kush from the pass near Bamiyan to the Bharogil Pass and thence follows the Pamir range to the greater Karakul. The height of the water parting on the Bharogil plain has been estimated by Captain Biddulph at about 12,000 feet. The mullah states that in traversing it for a distance of 5 miles, there was no appreciable rise or fall, and further it is said that from a point 1.5 miles short of the crest, the difference in height did not appear to be more than 200 feet. The Sarhad head of the Punjab branch of the Oxus is not more than 2 miles distant from the Geskul or Oikul, the longest source of the Aksu branch of the same river known as the Murghab. The principal source of the western head of the Punjab branch of the Oxus in Woods Victoria Lake is but 12 miles distant from the water parting between it and another branch of the Aksu. So little is his water parting marked by any defined physical feature that it was only after some difficulty that Trotter discovered it at a height of 420 feet above the level of Lake Victoria. There is also reason to believe that the Greater Karakul once gave off at one end a feeder to the Kashgar Darya of the Lobnar system and at the other a feeder to the Oxus. We have already seen that it is but a little difference in perpendicular height that determines the drainage between the Sutlej and Karnali and between the Nubra branch of the Shayok and the Karakash, so that where rivers have their sources in these elevated areas, it may be generally stated that a slight inequality in the surface, such as it is not possible to delineate on any ordinary map, is sufficient to determine the course of springs into channels that have a very remote debouch one from the other in the plains. The terms trough, channel, basin are in such cases often misleading, nor are the bounding ranges in these elevated regions marked with such well defined characters as are met with elsewhere. The Great Pamir is divided from the Alichur Pamir on the west by a range having an average elevation of only 3000 feet above the level of the sea, Victoria Lake, and from the Little Pamir by a similar range averaging about 2000 feet above the same level. The direction of the rivers depends, therefore, on the influence of much less relatively important masses of matter than are to be found at lower levels. The slight difference in level that determines the course of the head streams of the Karakash and Yarkand rivers on the Dipsang plains is sufficient to divert the former from their normal direction and drive them directly against the Kunlun range, where, finding a fault in the wall, they work their way through towards the plains. The influence of the law of gravity and the mechanical and chemical changes wrought by water are the sufficient causes for every form of river channel that is met with, and it is to their ceaseless action that even the stupendous gorges of the Indus, the Sutlej, and the Brahmaputra are due. Plains of Hindustan. Having concluded our review of the river basins and their relations to each other, we shall now proceed to examine the different parts of the area under our consideration. The great plain of Hindustan, which first claims our notice, is a vast flat extending with an almost unbroken surface along the foot of the Himalayan slope from the upper Indus to the Bay of Bengal. Its direction is from northwest to southeast over a distance of nearly 1,500 miles and having an area including its western branch along the Indus and its eastern prolongation into Assam of about 500,000 square miles. Indus Plain. On the west, it has its greatest development stretching along the Indus from the foot of the mountains to the sea, from northeast to southeast for a length of 750 miles. Its breadth from the Aravalli Hills to those west of the Indus is about 400 miles. The Aravalli Hills run in a northeasterly direction from the peninsula of Kathiawar until they lose themselves in the plain near Delhi. From this point, they run in a southeasterly direction connecting with the Vindhyas and in both cases constitute the abutments of the elevated plateau of central India. They thus form two sides of a triangle with its apex towards the north where it separates the Indus plain from that of the Ganges. The general slope of the Indus plain is southwest with, as we have seen, a slight depression towards the south until the influence of the northern slope of the Aravallis is felt when it gradually rises again. Taking a line along the Indus, we have Sehwan 117 feet above the level of the sea, Shikarpur 199 feet, Dehra Ghazi Khan 395 feet, Segra on the eastern bank of the Indus, opposite Dehra Ismail Khan 606 feet, and Khairabad opposite Kalabag, 750 feet. Following the 32nd parallel from west to east, we have Sandhi on the left bank of the Indus, 629 feet above the level of the sea, Lodri on the left bank of the Chenab, 657 feet, and Ramdas on the left bank of the Ravi, 796 feet. Further east, we enter the hills. Following the 30th parallel, we find Mare on the 71st meridian with an elevation of 386 feet, Noorsha on the 73rd meridian, 482 feet, and Pakka Sarava on the 75th meridian, 698 feet. The perfect uniformity of the surface is broken in the northwest by the small tableland between the Indus and the Jhelum, of which the salt range forms the abutment. These hills at the Sakesir station of the survey in the Jhelum district rise to a height of 4,994 feet above the level of the sea. They extend from Khairabad on the Indus to the Jhelum opposite Chilianwala, and thence those forming the eastern flank of the tableland, as well as a subsidiary range to the east of the Jhelum, turn abruptly northeast and connect with the outer range of the Himalaya near Bhimber at 1200 feet. The tableland itself is seldom more than 2 or 300 feet above the general level of the plain and presents an undulating, though tolerably even surface, broken occasionally by ridges which attain a height of from 2 to 3,000 feet. Indian Desert. The Indus Plain along the foot of the hills is sufficiently watered, but to the east and south, at any distance from the rivers, cultivation on an extended scale is only possible when the scanty rainfall can be aided by artificial irrigation. The latter tract, known as the Great Indian Desert, stretches through Batiana, Bikaner, Bahawalpur into Sindh. Tradition tells us that in former time it was a fertile and populous country studded with numerous cities and towns and inhabited by prosperous and civilized tribes. A recent writer states that there is nothing in history to show that the rivers of this tract ever contained much more water than they do now. Some diminution in their volume may have taken place during the lapse of ages from changes in the lower Himalayan range as well as from the destruction of forests and increase of irrigation. There is no doubt also a tendency to the obliteration of the lower part of their course, partly by the drift of sand and dust from the desert, and partly by the deposit of the silt brought down by the streams themselves, owing to the absence of the great river by which it would have been carried off to the sea. Between the Saraswati and the Sutlej are a series of broad channels, most of them a mile in width, of which those to the west appear to terminate in the valley of the Sutlej, while those to the east, which are also the more ancient, lead to the channel of the lost river Hakra or Sotra. The Kaggar now runs in an old bed of the Sutlej and was formerly an affluent of that river. The change may have taken place owing to some great cataclysm which formed a new bed for the river and left the old one for its tributaries on the east, and there is much to be said in favor of the identification of the Sotra channel with this old bed. At the present day, the water level in wells in this tract is excessively low, being often so deep as 300 feet from the surface. As the water, when procured, is often brackish, it is a matter of wonder that people are found to inhabit this country, which long ago received the name of Marusthali, the region of death. Gangetic Plain. The Gangetic Plain extends from the debouch of the Jamna from the hills to the head of the delta of the Ganges and lies between the great bend of the Himalaya and the northeastern slope of the tableland of central India, which here has a general elevation of about 1000 feet above the plain. The breadth of the plain varies from about 200 miles at Agra to about 100 miles at Rajmahal. The direction is to the southeast, but to the east of the Ganges, the courses of the rivers exhibit more southing. A general idea of the fall in height along the course of the Ganges may be obtained from the following figures. Saharanpur 903 feet above the level of the sea, Meerut 735 feet, Aligarh 610 feet, Agra 516 feet, Kanpur 517 feet, Allahabad 315 feet, Benares 255 feet, Patna 174 feet, Bhagalpur 159 feet, Bardwan 97 feet. Cross sections show little difference in height at any point. Bhatpura, below Mohan, at the entrance to the principal pass into the Dehradun, is 954 feet above the level of the sea. Following eastwards, the line along the foot of the hills, we have Hardwar 1016, Najibabad 860, Barhapura 910, Kashipur 750, Bilahri 760, Sigauli in Gorakhpur 300, Madanpur in Tirhut 230, and Amua 248 feet. Noting these figures on any good map and following the course of the rivers, a sufficiently correct idea of the general slope of the Gangetic plain will be obtained. At the termination of the hills near Rajmahal, the plain once more expands largely to the south and again presents an uninterrupted surface from the mountains to the sea. The length of this section is about 350 miles and its breadth from Rajmahal to the Brahmaputra about 150 miles, but increasing to about 300 miles along the coast at the head of the Bay of Bengal. The height varies from 100 feet, the level of the river Mahanadi at Malda, to 75 feet at Jelingi, the head of the Hooghly branch of the Ganges, and 31 feet at Chinsura. The Howrah station benchmark is but 18.2 feet above the level of the sea. These portions of the Great Plain, often though not very appropriately called the Valley of the Ganges, are intersected by the countless tributaries of that river and are under the full influence of the periodical rains. They therefore, as might be expected, comprise the richest, the most populous, and the most civilized districts of India, and in these respects form a striking contrast to the western parts along the Indus, which are doomed to perpetual sterility, not from any natural deficiency in the quality of the soil, but only from the great aridity of the climate. This barrenness is no doubt in a great measure due to the relative position of the Indus plain, to the higher ground around it, and to the prevailing winds. Matters which at first sight appear to be of little importance, but which are the efficient causes of the extremely dry climate that it possesses. Fluviatile action in erosion and deposition, productive of the alluvium and diluvium, terms so well known in the settlement records of these provinces, has clearly directed the course of the rivers in the great Gangetic plain. Mr. Ferguson, in an article quoted by the authors of the Manual of the Geology of India, shows that the rivers of the Ganges Delta oscillate in curves, the extent of which is directly proportional to the quantity of water flowing down their channels. Thus, the oscillations of the Ganges between Mungir and Rajmahal average 9.5 miles, and between Allahabad and Chunar only 3.7 miles in length. Further, when a great river runs through a low country, its course is considerably stayed by the sluggish expanses of stationary water, generally termed jheels in Bengal, and it is thus compelled to deposit its silt along its banks. Hence arises the phenomenon of a river passing through a country between banks that are higher than the adjacent alluvial flats, and the gradual increase of the banks until the stream makes its way through them to some lower level. Mr. Ferguson estimates that when the slope of a riverbed falls to less than 6 inches in a mile, A denuding river will be converted into a depositing river, and as the deposit commences at the bottom of the slope, the change proceeds upstream. Moreover, since the Ganges receives its more considerable affluents from the north, the left bank gradually increases and drives the main stream more and more towards the tableland of central India and makes the point of confluence of its affluents continually move upwards. This tendency is well marked in the Jamna in the Mainpuri district, where the old silted up bed is locally known as the Bhagna. In the Tarai below Kumaon, the same law prevails, and streams that in the upper portion of their course are denuding rivers in the lower portion where the check in slope occurs deposit their silt, form geels, and continually change their courses like the rivers of the Gangetic Delta. Assam Valley. The Assam Valley forms a narrow prolongation of the eastern extremity of the plain, partaking more, however, of the nature of a simple river valley liable to annual floods. It has a length of about 300 miles with a breadth of 30 to 40 miles, widening at its junction with the Gangetic Delta. It is shut in on all sides except the west by mountains. The characteristic of a sudden and total change along a definite line at the foot of the mountains from a broken hilly surface to an absolute flat which holds good throughout the other parts of the plain here no longer prevails. We frequently see small isolated hills standing out like islands from the general level surface, a phenomenon observable on a smaller scale where the Vindhyan range mingles with the plain. From Sadia, which is 440 feet above the level of the sea, the fall is gentle to Gauhati, which is placed at 163 feet, and Golpara, which is 150 feet. Taking a line along the foot of the hills, we have Titalia, 330 feet, Rajghat at the foot of the hills near Baksa, 220 feet, and the station at the foot of the hills below Divangiri, 670 feet. Figures which show a more sudden descent than those at similar positions under the western Himalaya. Bhabar. We shall now return to the plain between the Jamna and the Sarda, and more particularly to that part which lies immediately below the foot of the Kumaon hills. We find there a narrow belt of country, usually covered with forest and remarkable for the entire absence of water, a phenomenon eminently characteristic of this tract. The great rivers preserve their course with some diminution in their volume, but all the minor streams that have their origin in the lower hills on entering this belt soon lose themselves in the shingly deposit that constitutes the substratum. In time of flood, however, they often preserve a visible stream throughout their course, but this appearance lasts only so long as the cause exists. This belt of waterless forest land is called the Bhabar or Ukhar waterless forest under Kumaon, and has a breadth of from 5 to 15 miles. Though no stream or spring exists, the Babar is clothed with a magnificent forest, finding its nourishment in the few feet of alluvial matter that rests on the boulder and shingle deposit below. To the south of the Babar, the character of the country changes into a swamp devoid of trees and intersected by sluggish streams that rise from unhealthy morasses. Tarai. This tract is included with the Babar between the Ganges and the Fika under the general term Ban or Jungle. East of the Fika under Kumaon, where it apparently attains its maximum breadth, it is known as the Tarai, and under Nepal as the Taryani, with some specific addition as Morang, etc. It lies between the forest belt and the cultivated plains with an average breadth of about 10 miles under Kumaon, though varying much in different parts. Thus, we have between the plains proper under Kumaon and the foot of the hills two distinct belts of country, each about 10 to 15 miles broad, known as the Tarai and the Bhabar. The Tarai is characterized by the presence of reeds and grasses, showing the marshy nature of the ground. The streams carry off only a portion of the superfluous moisture and sluggishly run in tortuous channels, doubling back constantly in their courses. The soil consists of moist alluvial matter without a sign of rock either in fragments or in sight. In the Bhabar, on the other hand, no water rises from the ground. Throughout its whole extent, not a single spring nor any water can be seen, except occasionally where one of the larger rivers takes its course. In the rainy season alone, torrents cut into the ground, and the channels thus formed exhibit characteristic sections of this remarkable tract. We then find that there is but a thin covering of alluvial soil on a vast dry bed of boulders and of shingle, through which all rain that falls sinks rapidly and which absorbs in the same way all the minor streams of the outer ranges. Instead of reeds and grasses, we have here all the magnificence usually attributed to oriental forest scenery. Gigantic haldus, Adina cordifolia, and Kairs, Acacia catechu, rear their heads above a tangled undergrowth of creepers and thorn bushes, which present a barrier to progress that an elephant alone can surmount. Towards the hills, we find the Sal, Shoria robusta, and in Kota, great groves of mangoes, while patches of cultivation appear wherever irrigation is practicable. For this purpose, the streams of the lower hills are turned into artificial channels before they reach the shingle deposit, and even the lakes in the lower hills are dammed up to retain a sufficient supply of water for the Bhabar. West of the Kosi, however, there is little cultivation or irrigation, and the Bhabar there almost remains untouched by the plough. The actual slope of the ground between the Tarai and the foot of the hills is considerable, though not apparent to the traveler, except when he observes the rapidity of the current in the irrigation channels that line the road by which the Bhabar is crossed. Sivaliks. Before entering into more detail regarding the Bhabar and Tarai, there is yet a third feature characteristic of the tract below the Himalaya that must be noticed here as intimately connected with the other two, and this is the line of hills called the Sivalik or Sub-Himalayan. These will be well known to paleontologists in connection with the rich collection of fossil mammalian bones discovered in them by Dr. Falconer and Colonel Cotley. As a rule, they appear to rise abruptly and without any intermediate undulating slope from the apparently level surface of the flat country below to heights varying from a few hundred to 3 or 4,000 feet. They are composed of sandstones and conglomerates, and the dip of the strata is usually towards the general mass of the mountains at a low angle. The form of disturbance of the strata is very regular, producing broad normal anticlinal flexures, the axis plane sloping towards the mountains. Towards the plains, the slope has been weathered out so that plainswards the Sivaliks exhibit a steep face from which rise the highest summits of the range, while a long gentle declivity slopes inwards and forms a longitudinal shallow valley by meeting the foot of the next line of hills. The latter, as a rule, run on a line parallel to the Sivaliks, but at a distance of from 5 to 10 miles from them. Dunes. The bottom of this longitudinal depression is, as may be supposed, by no means continuous. In some places, it is cut through by the passage of the streams that drain the interior of the mountains. In others, it is quite obliterated by the near approach to each other of the two ranges that flank it and which usually form distinct lines. This is, moreover, a structural feature and not due simply to denudation. In the country between the Sutlej and the Kali, these valleys are called dunes, and under Nepal, according to Hodgson, they are called maris. They have been confounded by some writers with the Tarai, which, as we have seen, is quite distinct. The lower part of the dunes generally appears to be covered with a deposit of boulders and gravel that slopes somewhat steeply from the Himalaya towards the Shivaliks, so that the whole bottom of the valley is considerably raised above the level of the plain without. In consequence of this elevation, the outer hills, when viewed from the interior of the valley, as from Mussoorie, present a very insignificant outline. The drainage of these valleys usually collects along their longitudinal axis and either falls into some of the larger streams that cross them, or less frequently finds an independent exit for itself into the plains by a sudden bend to the south through a break in the outer range. Owing to the considerable elevation of the dunes above the plains down to the level of which the drainage finds its way in a very short distance, the unconsolidated strata that form the floor of these valleys are constantly cut through to a great depth by watercourses. Consequently, the surface, though often presenting an apparent flat for several miles together, is frequently broken up into steps which, on the whole, are tolerably level but at different heights, the one above the other. This phenomenon is not uncommon and is constantly observed along rivers that are eroding their banks. To the same causes also are to be attributed the practical impossibility of procuring water by means of wells in the dunes, a difficulty which mainly arises from the thorough desiccation of the gravelly soil by the deep drainage. Extent of the Bhabar. We have not sufficient information to state distinctly how far the Bhabar extends both east and west along the foot of the Himalaya, but the following indications would lead us to suppose that this phenomenon is inherent in the relations of such a mass as the Himalaya with the subjacent plains. Under Nepal, it is called the Jari or Bhavar, and according to Hodgson, extends from the Kali to the Mechi on the east with the same general characteristics as under Kumaon. Eastward of the Tista, according to the same writer, the Bhabar and Tarai do not exhibit the same parallelism to the line of the Himalaya, but show themselves plainwards like an irregular series of salient and resalient angles resting on the mountains, or like small insulated plateaus or high undulated plains, surrounded in both the later cases by low swampy land analogous to the Tarai. An example of the former is found in the plateau called the Parbat Jowar on the confines of Assam and Rangpur, which is considerably elevated, quite insulated, remote from the mountains, and covered with sal, the characteristic tree of the Upper Bhavar. Again, we have undulating plains such as those that occur around Dinajpur and to the northwest and northeast of Siliguri, all of which may be identified with the Bhabar. In all these cases where the detritus bed thins out, a moist tract is met with, though in no case so marked as to the westward. Herbert affirms the general applicability of his remarks regarding the submontane tract below Kumaon to the entire country between the Ganges and the Sutlej, and parish to the tract further west between the Sutlej and the Beas. There is no well-defined line dividing the area of swamp from the Bhabar proper between the Sarda and the Ramganga. To the east in the Tallades Bhabar, where the streams seek the Sarda directly, there is less Bhabar, and the swamps that exist are not so extensive, but at the same time are more formidable, being often surrounded by tangled masses of canebrake. The Dhyanirao Bhabar also is comparatively narrow, and it is not until we come to the Chakhata Bhabar that we get a breadth of 8 to 12 miles that lasts until the Fika River is reached. The Tarai exists all along the track to the south of and parallel to the Bhabar from the Sarda to the Fika. But west of the Fika, it loses its characteristics and can only be traced in the closeness to the surface of the water level in wells. Westward of the Fika, the Bhabar or waterless tract also narrows and the sal forest does not descend more than 6 miles from the foot of the hills, and a few miles further west it has not a breadth of 2 miles. The Bhabar, however, exists and is broader than the present sal forest, of which much has been cut down of late years. Its presence is shown by the absence of wells, and similarly, the Tarai appears in a line of wells which, with water at from 3 to 6 feet from the surface, running parallel to and bordering on the Babar. This limitation of both the Babar and Tarai is conterminous with the commencement of the Patli Dune, which has detained the greater part of the detritus that is elsewhere spread out below over the plains. From the Fika eastwards to the Sarda, where these tracts attain their maximum importance, there are no dunes, properly speaking. For the Kota dune presents no great barrier to the south, and further east, the Shivaliks are so blended with the outer range that a geologist alone can trace their sequence. In this fact, we have an illustration of that portion of Hodgson's theory that gives a narrow extent to the Bhabar below the dunes and a broader range where there is no dune to intercept the debris from the hills. The facts that we know regarding the Bhabar to the north of the Saharanpur district further confirm this deduction. The Bhabar in Turkestan. In eastern Turkestan, we find a similar phenomenon. Trotter tells us that the Sagon River, which has its source at the eastern foot of the Teret Pass, after it reaches the plains north of Kalti Ailak, wastes away and leaks through crevices in the stony ground. The Hakim of the latter place assured him that wells had been often sunk but proved of no use. Trotter writes, this diminution in the size of rivers as they descend is one of the chief characteristics of the country and occurs in all minor streams that have come under my notice. Of course, much of this is due to irrigation, which necessarily carries off large quantities of water, but the stony soil has also much to answer for. On the other hand, the frequent appearance of large springs giving considerable supplies of water and often issuing from the open plains at long distances from the mountains may account in a great measure, if not fully, for the water thus lost in its early infancy. Here we have the existence of a Babar and Tarai vouched for by competent authority in the Yarkand and Kashgar country. The same phenomenon, but on a larger scale, was found by Przewalski to characterize the tract between Korla and Lobnar. A belt of country about 3 to 4 miles wide, consisting of an undulating plain covered with a pebbly or gravelly soil and totally devoid of vegetation, runs parallel to and at the foot of the Kuruk, a low, waterless, and barren range. Beyond this stony margin, which appears to define the shoreline of an ancient sea, lies the great desert of drift sand, amid which salt marshes exist wherever the moisture comes to the surface. The same pebbly plain was found under the northern slope of the Altin Thag, the northeasterly continuation of the Kunlun Mountains between the 90th and 92nd meridians, and north of and below the stony margin, the usual salt marshes occurred. The latter are also found at the foot of the northeastern portion of the Tibetan tableland in Saidam. It would therefore appear that tracts analogous to the Babar and Tarai of Kumaon surround the entire Himalaya Tibetan mass and that they vary in character according to local influences. Hodgson attributes the distinctive character of the Babar as a whole to the vast mass of diluvial detritus which was shot from the mountains upon the plains like gravel from a cart at some great geological epoch and which has been, since its deposit, variously and often abraded both in degree and direction by oceanic and in a far less degree by ordinary floods. Another writer considers that this theory of Hodgson's appears to be a reasonable explanation of the existence of these great beds of shingle, sand, and boulder all along the foot of the mountains. It is argued that no rivers can have laid out such a vast deposit, and we can only conclude that we see here the limits of an ancient ocean that once washed the base of the Himalaya. The boulders and shingle are spread out only for a distance of 10 or 15 miles from the mountains from which they are derived, while the finer particles of sand and clay are carried much farther. Great variations in the depth and breadth of the deposit occur due, in a great measure, to local causes. One which apparently has had a great influence is the existence or otherwise of the Shivalik range. Where there was no sandstone range to intervene between the mountains and the plains and collect the detritus within their contained dunes, the deposit is broader and not so thick. Where there was such a barrier, it has been carried less southwards and exists in great accumulations between the barrier and the mountains. Again, where no range existed but only spurs sent forth like bent arms upon the plains from the mountains, Hodgson observes that the embayed detritus is simply deeply piled and lofty within such spurs and thinly and unequally spread without them by reason of the action of the spurs on the current. He notices as an example of this form the debris embayed by a spur on the road to Darjeeling by Pankabari, where it is accumulated to several hundred feet, and where, moreover, there is outside the spur a succession of terraces, apparently due to oceanic forces. Further, whereas from Gauhati to Sadia, there was not room upon the plains for the free spread and deposit of the detritus, owing to large and rapid rivers and to other chains, both proximate and parallel to the Himalaya, the phenomena created elsewhere by the more or less unrestricted spread of the Himalayan detritus over the plains would necessarily be faintly, if at all, traceable. Lastly, if at the time of the descent of the debris there existed a great dip in the Gangetic plain from the northwest to southeast, the lithologic character as well as the distribution of the debris would be materially affected thereby, for the subsiding oceanic current would have a set from the former to the latter quarter and would continue to lash the gravel into sand and here to deposit both in a series of terraces, there perhaps utterly to displace both in the latter quarter long after the former had emerged from the waves. Fluviatile theory. The oceanic theory of Hodgson is not accepted by the majority of professed geologists. Mr. W. Blandford writes, there is absolutely no proof of any sort or kind that the whole Indo-Gangetic plain has at any time been a marine area. But there is equally no proof that it has not. It has been shown that in Eocene times, the sea occupied the Indus Valley as far as the foot of the Himalaya and extended along what is now the base of the mountains as far east as Kumaon, and also that marine conditions prevailed to the northwest throughout a great part of the tract now occupied by the Assam range. But it was also pointed out that in the area between Kumaon and the Garo hills, no trace of marine formations had been found. Yet it is difficult to understand if the Gangetic plain was a sea basin, why no marine beds occur. It is true that the northern border of the plain, throughout the most important part of the intervening space in Nepal, is unfortunately inaccessible to Europeans. But still, if the Gangetic plain in any way corresponds to the Eocene Sea, as the Indus plain doubtless does, why are no traces of marine beds found to the south of the valley on the margin of the peninsular area, as they are in the desert to the east of the Indus? In the Brahmaputra plain also, no marine deposits of tertiary age are found. In the plain itself, only fluviatile deposits have been detected, and the marine Eocene and Miocene beds are confined to the southern slope of the range, forming the southern watershed of the valley. Mr. Blandford considers the post-tertiary formation of these provinces to be clearly river deposits. The later tertiary formations belonging to the Sivalik series contain reptilia and mollusca, but not a single marine shell. It is impossible to tell what beds may be concealed below the Indo-Gangetic alluvium, and marine strata may exist to an enormous extent without appearing at the surface. It is also unquestionable that the amount of information hitherto derived from borings is very small indeed, but so far as that information extends, and so far as the lower strata of the alluvial plain have been exposed in the beds of rivers, not a single occurrence of a marine shell has ever been observed, nor is there such a change in the deposits as would render it probable that the underlying strata are marine. The only evidence known in favor of marine conditions having prevailed during the deposition of any portion of the Gangetic alluvium is the occurrence of brine springs at considerable depths in a few localities. These springs, however, are not numerous, and without additional evidence, it is impossible to look upon them as proofs of marine deposits. At the same time, it is by no means impossible that the sea occupied portions of the Sindh and Bengal long after the plains of Upper India were dry land. On the whole, Mr. Blandford thinks that the oceanic theory wants further support, that the fluviatile theory is the only one that fits in with the present state of our knowledge, and that the depression of the Gangetic plain is of contemporaneous origin with the disturbance and contortion of the Himalayan ranges, and that the physical features of the two areas are closely connected. No important borings have ever been made in these provinces, and nothing has ever been discovered, so far as we are aware, to show that the older theory is the correct one. The newer theory is further supported by the discovery of the buried town of Behat in the Saharanpur district, some 17 feet below the present level of the country and containing coins of the commencement of the Christian era, thus showing what can be effected by fluvial action in 18th centuries. Tarai. We have already seen that the distinctive features of the Tarai are not found west of the Fika river. If we except a small tract on the left bank of the Ramganga, the condition of which, however, is probably due to defective drainage in that particular part and might occur in any other place. The existence, therefore, of the Tarai as a distinctive feature must be due to local causes capable of explanation, but the imperfect nature of our knowledge will only allow us to guess at them. Herbert described the Tarai as defined in its southern boundary by a rise or step which runs parallel to the common boundary of mountain and plain land. He observes the height is variable, occasionally as much as 30 feet and sometimes sudden and steep. Modern research can discover no well-defined boundary beyond the chain of springs which sometimes approach within a couple of miles of the foot of the hills and sometimes are separated from them by a belt 15 miles wide. In no case is there any such rise or step as described. Hodgson also accepted the existence of a longitudinal trough running parallel to the Himalaya as a characteristic of the Tarai, which he held to be a natural depression in the plain and thus accounted for its peculiarities. This theory, however, is opposed to the results obtained by leveling operations and appears to be based on an entirely erroneous idea, the fact being that the drainage of the higher country, beyond which has been lost in the absorbent strata of the Babar, here breaks out again in a line of copious springs which collect into swamps in the Tarai. This feature has also somewhat plausibly been accounted for by the existence of an impervious stratum below the absorbent boulder detritus, and as the latter gradually thins out, the finer and less permeable silt underlying it approaches nearer and eventually reaches the surface, bringing with it the water that has been absorbed by the shingle talus and has been retained by the impervious silt. Although this explanation seems reasonable so far as it goes, it must be remembered that the swampy Tarai extends only from the Fika to the Tista and we must therefore look for some peculiarity in this part of the plain which does not exist elsewhere, by which we may account for the existence of swamps exclusively in this particular locality. In a recent note, Mr. Lauder gives the following section of the Babar and Tarai image, which has to be glanced at by pausing the video. His experience of this tract has led him to consider that, whatever may be the nature of the underlying formation, the surface beds are solely due to fluvial action. The mountain torrents along the foot of the Kumaon hills bring down every year a vast amount of debris which is spread out over the surface, now on one side of their previous course and again on the other. This irregular deposition itself compels the torrents to change their beds from place to place until, as now obtains, the points where they debouch from the hills are marked by more or less irregular, great, fan-shaped boulder and gravel deposits. The clayey or semi-soluble particles are necessarily carried farthest and are readily deposited not only where there is a check in the slope, but where the current is impeded by the tortuous nature of the channel, which itself naturally assumes that form under these conditions. Here, during the rains, the streams saturated with clayey silt overflow their banks, form new channels, fill up old ones, and create the tarai. Above this deposit of clay, we find one of clay combined with sand, in which, however, the latter predominates. From this bed issues the line of Tarai springs that flow uninterruptedly throughout the year, and its margin marks the northern boundary of the Tarai. Above, we meet beds of sand and gravel or gravel and boulders as we approach nearer to the hills. A longitudinal section taken at the top of the Babar will show that the hill torrents in the upper portions of their course run along a ridge formed by the debris transported by themselves, whilst a similar section of the Tarai, as shown in figure 2c, would show that, as a rule, the river channels are found in depressions below the general level of the country. The geological section, as shown in figure 2a, shows the gradients of the present ground surface on the road between Bareilly and Rani Bagh, and from them it will appear that in the boulder region, deposition takes place at a slope of 66 feet to the mile, whilst the clay is not deposited until the descent falls to about 8 feet in the mile. It may fairly be assumed that these are the usual angles of deposition of the materials, and that they have obtained since the degradation of the lower hills and the resulting deposition below them commenced. If so, a series of proportionate curved lines running almost parallel to the present ground surface may be taken to represent the ground surface of succeeding periods, and such portions of these lines as may be similarly inclined with the present Tarai portion, that is, at the same angle with the horizon, will evidently represent the Tarai or clay deposit as it then existed. A line intersecting all these beds at the several points of junction of the clay with the sand and clay will represent the present impermeable bottom of the Babar Basin and account for the line of springs upon the surface where the stratum of sand and clay crops out. The upper boulder and gravel beds permit of the filtration of water freely through them to the clay, at the same time acting as a capillary reservoir to keep up the dry weather supply to the springs below. We have further evidence in support of this theory in the fact that the Tarai proper does not extend westwards of the Fika river. Between the Fika and the Sarda, there are no dunes, for the Kota dune has its southern boundary broken through by rivers, and along the entire tract, numerous torrents find their way directly to the flat country below. The proximity of these torrents to each other causes the accumulation of debris to exhibit a continuous appearance, which seems to have suggested the theory of a marine origin. To the west of the Fika river, the drainage of the lower hills is carried off mainly by streams which collect the drainage within the sub-Himalayan range and seek the plains in one well-defined channel. The Ramganga is the great arterial drainage channel for lower Garhwal, and between it and the Ganges, the only considerable stream is the Ko, which has a small strip of Babar below it. In eastern Kumaon, the Ladhia serves a similar purpose, and where in its course towards the Kali it approaches the plains and does not allow of any considerable stream from the southern face of the outer range. Both Bhabar and Tarai are narrow, and as this confluence of the Ladhia on the east and the Ramganga on the west decreases, the Bhabar and Tarai increase and eventually attain their maximum breadth where that influence is least felt. Where rivers discharge large volumes of water like the Ganges and the Sarda, and in a lesser degree the Ramganga and Kosi, the velocity at their debouches from the mountains is much less than that of the minor torrents, owing to their having cut back and more deeply their channels within the hills, so that only the lighter particles of eroded matter are carried onwards, whilst the boulders are left behind at their natural point of deposition. Hence, near these larger rivers, it curiously happens that the width of Babar and Tarai contracts in a certain ratio, and in the case of the Ganges disappears. This explanation is supported by the results obtained during the contour survey of the Tarai. The second diagram in figure 3 shows a portion of the country between the Dhora river and the Bhuta stream taken from the survey maps, and will illustrate the intricate nature of the leveling operations and show why in some places the stream double back on their original direction and exhibit the tortuous courses so characteristic of this tract. Figure 3. This should be read by pausing the video. Okay. It will also be observed that there is a sudden check in the slope where the Tarai commences. To the north in the Bhabar, the slope is from 60 to 100 feet in the mile, and in the Tarai, it falls to about 10 feet. These are the adequate causes of the existence of swamps, and though the neglect of artificial obstructions made for the purpose of utilizing the water for irrigation may doubtless aggravate the natural defects of drainage, it would probably produce no effect whatever were it not for the peculiar physical conditions that exist here. To the west, between the Indus and the Ganges, the great arterial drainage lines collect within the hills and run off directly from them, the general fall of the surface receiving no such check as is found under Kumaon. The same is true of the country to the east along the head of the Bay of Bengal, and in the narrow valley of Assam, the Brahmaputra runs in a deep bed at right angles to the natural course of the streams from the hills, and thus forms a perfect system of cross drainage that does not allow of the formation of swamps. Sivaliks. The Sivaliks appear to have a more or less definite existence along the whole of the Himalaya from the Indus to the Brahmaputra, presenting modifications of the same general features along the entire line. To the eastward of the Tista, they are wanting locally, a fact which it has been suggested is due to denudation, as in the case of the partially obliterated barrier to the south of the Kota Dune. As the Sivaliks will be noticed hereafter in the chapter on the geology of Kumaon, we need not describe them here. Between the Jamna and the Sarda, they are found as the southern boundaries of valleys as far eastwards as the Nihal river, and thence onwards they almost coalesce with the outer range of the lower Himalaya. Dunes. Of the dunes or valleys between the Shivaliks and the Himalaya, that known as the Dune or Dehra Dune from the town of Dehra is not only the most remarkable but the best known. Since the physical geography of this tract will be considered in more detail hereafter in the notice of the Dehradun district, it will be sufficient for our purpose here to note that the dune a little to the west of the town of Dehra is divided by a ridge that serves as a water parting between the Asan, a tributary of the Jamna on the west, and the Suswa, a feeder of the Ganges on the east. The tracts drained by these rivers are known respectively as the Western and Eastern Dunes. The two taken together have a length of about 45 miles and an average breadth of 11 miles. The east end of the Dehra baseline of the Great Trigonometrical Survey on the extremity of one of the spurs of the Ghati range, about 1 mile west of Mahobawala, is 1957.65 feet above the level of the sea. Mahobawala itself is 2096.56 feet and Dehra is 2323 feet. The junction of the Suswa and the Ganges is little more than 1000 feet above the level of the sea, giving a considerable fall for that stream between Dehra and the Ganges. A well sunk by Mr. Shore, when administrator of the dune, attained a depth of 221 feet before a plentiful supply of water was met with, and even at that depth, the nature of the deposit was the same as at the surface. The greatest thickness of the deposit is observed near the central ridge. It thins out to the west and east along the course of the Asan and the Suswa, and according to Herbert, may be observed in the beds of the Jamna and Ganges resting on sandstone. Next, on the west comes the Kayarda Dune, some 6 miles broad and 25 miles long, to the water parting between the Jamna and the Kaggar systems. Beyond it, we have the Pinjor Dune, which has in parts a breadth of 6 miles and a length of about 30 miles. The Sivaliks here are neither so broad nor so high as to the south of the Dehra Dune. The Pinjor Dune is divided into two parts, the eastern and western dunes, by a ridge similar to that observed in the Dehra Dune, and which attains an elevation of 2,402 feet above the level of the sea. To the east, the drainage flows into the Kaggar, and to the west into a tributary of the Sutlej. Mansi Devi, a temple in the plains just within the dune, has an elevation of 1,263 feet, giving a fall to the rivers within this dune similar to that found to exist within that of Dehra. Okay, there is a table here which I think should be read by a glance. By passing the video, this table can be read. Okay. Ganges to the Brahmaputra. East of the Dehradun, we have the Patli Dune, also divided into two parts, but by a depression, not a ridge, a fact possibly pointing to its being a valley of denudation. That to the west, which is drained by the Sona Nadi, has a slope eastwards parallel to the Himalaya and is known as the Kotri Dune. That to the east, which is drained by the Ramganga and has a slope to the west in the same direction, is called the Patli Dune. The two rivers meet just before their waters take a bend to the south at an elevation of about 950 feet above the level of the sea. A few miles eastward of their confluence, the valley of the Patli Dune shows an elevation of 1,200 feet on the right bank of the stream and thus allows a considerable fall to the Ramganga in a comparatively short horizontal distance. The peaks of the Shivaliks to the south along this entire line seldom rise above 2,500 feet, whilst the plains at their southern base average between 8 and 900 feet. Further east comes the small Kota Dune between Dikuli and Kali Dungi, much broken up by torrents and having its southern boundary cut through by the various hill streams that cross it at right angles. From Nainital to the Sarda, the sandstone ridge that represents the Sivaliks is so close to the Himalaya that the geologist alone can discern the connection. The dunes are here reduced to deep longitudinal gorges and low gaps corresponding with a leading geological boundary that between the old slaty and schistose rocks of the mountains and the massive tertiary sandstones of the Sivaliks. Further east, according to Hodgson, the dunes are represented by the Salian Mari, the Gongtali Mari, the Chitwan Mari, the Makwanpur Mari, and the Bijaypur Mari, all under Nepal. With the exception, however, of the dune lying on the road to Kathmandu, none of these have been subjected to scientific examination. On this track, writes Mr. Medlicott, very complete representatives are found of the two sub-Himalayan ranges and their intervening dune on Mari. The Churya Ghati range is structurally a facsimile of the original Sivaliks. At the outer base at Bichiako, there are some earthy rusty beds all greatly crushed. The dip soon settles down to 30 degrees to north-northwest, maintaining the same angle steadily to the top of the pass. This is the typical structure of these detached sub-Himalayan ranges, the flat inner half of a normal anticlinal flexure. The range is about 4 miles wide. Throughout the Sikkim and Bhutan, Dwars, there is no representative of the Shivalik hills and therefore no dunes, but in the Dikrang basin of the Dafla hills, Colonel Godwin Austen discovered two well-marked ranges of sub-Himalayan hills with an intervening dune. We have now seen that the first characteristic features met with in advancing from the plains to the Himalaya are the Tarai, Bhabar, Shivalik range and dunes or valleys, and that though not continuous and indeed occasionally altogether absent, they are taking the whole range characteristic of the relations of the Himalayan mass with the subjacent plains. Lower Himalaya. Crossing the dunes northwards towards the snows, we meet the outer ranges of the lower Himalaya. They have a general elevation of about 7,000 feet above the level of the sea, while the highest summits along the line reach between 8,000 and 9,000 feet. This generalization, though giving the nearest approach to accuracy that the state of our knowledge permits, is only approximate, for we know very little regarding the outer range between the Sarda and the Brahmaputra. There is this peculiarity in Kumaon that the outer range first crossed by the traveler is of considerably higher elevation than the intermediate ranges crossed between it and the outlying spurs of the great snowy range itself. We have said that we hold the entire Himalaya to be but the southern slope of the great Tibetan plateau, that however rugged and furrowed this slope appears, it is homogeneous throughout. We reserve for the district notices the purely geographical description and will here try to answer the questions that naturally arise regarding these mountains as a whole. What have geologists been able to discover regarding their history and the materials of which they are composed, and are the causes at work sufficient to produce such very varied results as are here exhibited? In attempting to answer these questions, we must refer to well-known principles which have been found true in Europe and apply with equal or even greater force to the phenomena observable in the Himalaya. Goodness, why is my phone behaving oddly? Okay, it has closed. Sorry. Okay. We are at page 100. Let me begin from here. I don't know where I actually lost the thread. There is this peculiarity in Kumaon that the outer range first crossed by the traveler is of considerably higher elevation than the intermediate ranges crossed between it and the outlying spurs of the Great Snowy Range itself. We have said that we hold the entire Himalaya to be but the southern slope of the Great Tibetan Plateau. That, however rugged and furrowed this slope appears, it is homogeneous throughout. We reserve for the district notices the purely geographical description and will here try to answer the questions that naturally arise regarding these mountains as a whole. What have geologists been able to discover regarding their history and the materials of which they are composed, and are the causes at work sufficient to produce such varied results as are here exhibited? In attempting to answer these questions, we must refer to well known principles which have been found true in Europe and apply with equal or even greater force to the phenomena observable in the Himalaya. Without trespassing on the domain of the professed geologist, we may briefly summarize the facts observed regarding the Himalaya as a whole. We have seen that the outer range forms a geological as well as a physical boundary under Kumaon. The whole mountain mass may be divided into three great belts. First, the sub-Himalayan tertiary sandstones outside the Himalaya proper of geologists and which have a considerable development west of the Jamna. To them belong the Shivaliks and the Sirmur series on which the hill sanitaria of Kasauli, Dakshai and Subhatu are built. Secondly, a belt of limestone and slate forming the outer range of the lower Himalaya on which the hill sanitaria of Simla, Chakrata, Masuri, Landaur and Nainital are situate. Thirdly, the crystalline rocks with granitic intrusions that form the remainder of the lower Himalayan region, as well as the line of snowy peaks, and across the British frontier to the north of Kumaon, the Paleozoic and secondary rocks of Tibet. Thus, we have as the materials of the Himalaya the two great classes of rock known as the stratified or bedded and the crystalline. To the former belong the limestone, sandstones, and slates that have been derived from the waste of the older rocks, and to the latter the granite, gneiss, and schists which occur in masses. Materials of the Himalaya. The core or nucleus of all great mountain masses is formed of crystalline rocks, while the stratified rocks enter largely into the composition of the lower subordinate ranges. This is true of the Himalaya, Alps, Pyrenees, Rocky Mountains, and indeed of all the great mountain systems. A glance at the geological map given hereafter will show more clearly than any description the arrangement of these rocks in Kumaon. One of the fundamental principles of geology is that the sites of all the great mountain masses of the world at one time formed a part of the bottom of the sea. K2, Nanda Devi, and Mount Everest, the last of which exceeds a height of 29,000 feet above the level of the sea, at one time apparently formed parts of the bed of an ancient ocean. For the crystalline rocks have arisen either from the gradual consolidation of materials which had been fused deep within the crust of the earth, or from the influence of subterranean water combined with the earth's internal heat out of earlier sediments such as sea mud and sea sand, which in the course of time had sunk down and been covered by many thousands of feet of later deposits. Geologists tell us that while no important movements except small and partial changes of elevation can be traced in the peninsular formations of India, the whole of the gigantic forces to which the contortion and folding of the Himalaya and the other extra peninsular mountains are due must have been exercised since Eocene times. The sub-Himalayan beds were deposited upon uncontorted Paleozoic rocks, and although a part of the Himalayan area may have then been land, the direction of the ranges is clearly due to post-Eocene disturbance. It has also been shown that the movement has been distributed over the Tertiary, post Tertiary, and Pleistocene periods. It has been suggested that upheaval still goes on as earthquakes are of common occurrence along the line of the Himalaya and as far westwards as Kabul. Three distinct shocks were felt at Nainital in April 1880, and Srinagar in Garhwal was almost destroyed by a great earthquake in 1803. A recent traveler, Monsieur Svetsov, attributes the contraction of the great Karakul Lake on the western Pamir to a similar cause and says that the connection of the Tian Shan with the Pamir is due to an upheaval which geologically is of recent date and is still progressing. At the end of the Cretaceous period and at the beginning of the Tertiary period, the Tian Shan was separated from the Pamir by a strait with rocky islands, the marine deposits of which are found beyond the Tuz Ashu Pass. It is startling to the uninitiated to be told that the mighty mass of the Himalaya, as it now appears, is a formation younger than the comparatively insignificant hills of the Deccan or Deccan and central India. The same, however, is said of the Alps, Pyrenees, Andes, and Rocky Mountains, all of which received their chief upheaval in tertiary times. Eocene period. According to Mr. Blandford, it is probable that the crystalline axis of the western Himalaya, which apparently terminates in the Dhauladhar peak, the western extremity of the snowy range seen from Simla, coincides with the shore of the ancient Paleozoic continent of which the Indian peninsula formed a portion. If this be a correct view, the cis Himalayan Paleozoic rocks are in a great part of freshwater origin, whilst the marine Paleozoic formations are found throughout the extreme north of the Punjab, Kashmir, and the neighboring countries north of the Dhauladhar and crystalline axis. In Eocene times, the peninsula of India was part of a great continent probably united with Africa. To the east was a great sea extending up the Assam Valley along the southern base of the Garo Hills and then southward throughout a considerable area west of the Irrawaddy in Burma. There was another sea to the northwest, covering a great part, if not the whole, of Persia, Baluchistan, the Indus Plain, and extending as far northeast as Garhwal, and an arm of this sea extended up the Indus Valley into Ladakh. The Himalaya and perhaps Tibet, wholly or in part, were raised above the sea, but there is no evidence to show that they had then attained any unusual elevation. In later Eocene times, the Himalaya had risen sufficiently to send back the sea boundary to the north of the Punjab, and in Miocene times, the marine area was still further contracted. The existence of a sea in these places is attested by the presence of marine deposits and shells, and this discovery clearly shows that not only did the sites in which they occur once form the bottom of a sea, but that the difference in height now observed between them and the level of the sea must be greatly added to in order to arrive at the true measure of the upheaval that has since occurred. The work of denudation that continually goes on shows us that the present summits of the mountains must, in the course of time, have lost a considerable portion of their substance, and in the next place, we cannot suppose that the marine shells now found lay exactly at the sea level. The bed of the Great Sea may also have been subject to successive periods of depression and elevation before the Eocene period without greatly altering its height. Professor Geeky tells us what the forces are to which these marvelous results are due. The upheaval of the seafloor into land seems to have been due to a cause which has been going on from the earliest geological times and which is still in progress. It is believed that originally this planet possessed an enormously high temperature, that indeed it was thrown off from its parent sun with a temperature probably even much fiercer than that of the sun at present, and that it has since been gradually cooling and contracting. The external crust of the Earth, varying greatly in structure and otherwise, has yielded unequally to the strain of contraction. One result of this process has been the elevation of portions here and there into long ridges, forming the continental masses and mountain chains. You may illustrate this production of lines of elevation along a generally subsiding surface by what takes place when an apple dries. Its surface contracts and wrinkles, most of the skin sinking inwards, but at the same time unequally and leaving intermediate ridges to stand up. So, in the gradual contraction of our planet, wrinkles have arisen on its surface. It is these wrinkles which form our mountain chains. But such a subsidence of the crust could not have taken place without a very great deal of folding of the rocks. Descending nearer to the Earth's center, the various layers of the crust had a less diameter to fill. They could only accommodate themselves to their new position by being crumpled up so as to occupy less space, or by being cracked across so as to allow some parts to be pushed above others. We find that both these results have been produced, and the records of the Indian Geological Survey teem with illustrations of them. Mode of mountain formation. One other fact is noticed by the same writer in connection with the crumpling up of the mountains, and that is that this process has been the means of bringing up the crystalline rocks. Before the time of the crumpling, the whole future mountain area was covered with one continuous sheet of marine strata. But as the mountain chain began to form, the central portions came to be more and more compressed, puckered, and crystalline, some parts being squeezed up, whilst intrusive masses and veins of granite and other crystalline rocks were injected amongst the intensely altered strata along the central nucleus or core. It was during this process, doubtless, that the crystallization of the gneisses and schists took place when they passed from their original character of fragmentary bedded rocks and assumed the peculiar crystalline texture which they now present. We have already noticed that there have been successive upheavals of the Himalayan mass through the tertiary and post-tertiary and even the Pleistocene periods, and the effect of these upheavals on the form of the mountain ranges must have been considerable. Supposing, with Professor Geeky, that a whole mass of sedimentary rocks has been upheaved into land as a mountain chain, we find that on the outskirts of this elevated area, sedimentary deposits will continue to accumulate in the sea. If, in the course of the slow secular contraction of the planet, the upraised tract subsides, a new set of strata will be laid down upon the upturned edges of the older rocks. It is evident that in every junction of this kind, some considerable interval must have elapsed between the formation of the older series of rocks shown as A in figure 4 and the newer series shown as B in figure 4. In the course of time, the region having once yielded to the strain from terrestrial contraction will probably yield again and a new upheaval will take place. The series B will now be raised up together with A, and another series C will be laid down in turn upon its edges. Subsequently, the same fate will befall the group C. These three sets of differently inclined strata would fix for us three successive periods of upheaval. This simple explanation shows how very varying must be the results of successive periods of depression and upheaval, and especially when, as in the case of the Himalaya, such an immense area has been subject to disturbance. We have now seen that the primary factor in mountain architecture are the great changes in the Earth's crust by which mountains have been formed, and the bedded deposits have become rocks, and eventually, as the process of upheaval went on, have been crumpled, folded, crystallized, and fractured. In this process, lateral pressure has been the chief agent, and this has been exerted simultaneously from different sides in the case of the Himalaya, at least in the Pleistocene period. No better examples can be given than those enumerated by Mr. Blandford as characteristic of the western area. Here we have amongst the mountain ridges that encircle the Indus plain and comprise Pliocene beds, ranges running north and south such as the Kirdar and Sulaiman, east and west as the Mari and Bhukti and the Afridi hills, northwest and southeast as the Pir Panjal, northeast and southwest as the eastern Salt Range and Karyan hills. And many intermediate directions may also be traced independently of curved ridges. Of the extent of these lateral thrusts, an example will be found to the west of the Indus. Taking the Persian area and that of the Himalaya and Tibet, the mountain ranges fall roughly into two great curves convex to the southward, but the deeper western curve has produced the smaller mountain ranges. That a gigantic lateral movement has taken place in the apex of the western curve is, however, shown by the fact that for nearly 150 miles between Ghadar and Jalk in Balochistan, the track traverses beds all apparently of tertiary age at right angles to their strike, and that all these beds are vertical or nearly so. The contraction in breadth, or in other words, the lateral movement, must have been great to have converted horizontal formations into a series of undulations with dips so high as those seen in the Balochistan ranges. The terms at our disposal to denote the relations of magnitude and adequately to depict the changes that have been wrought during such a period are utterly insufficient to convey a correct idea of what has taken place. Perhaps Professor Geeky's my simile of the dried apple is as far as we can go without entering into scientific details that belong to the professed geologist. Mountain sculpture. Only second in importance to subterranean influence in the formation of mountains are the sub-aerial tools of the great sculptor, the different forms of water, ice wedges, glaciers, snow, rain, and rivers. It is impossible to say what may have been the appearance of the mountain ranges when first formed, but we have every reason to believe that usually the process was gradual and that at once the denuding influence of the different forms of water came into play. Nature, from the time the first atmosphere existed, has ever been at work tracing lines which gradually work into gorges, ravines, and valleys, weathering peaks and rounding ridges, and producing those alterations in the general appearance of the mountains that, on a very small scale, are familiar to most of us in a neglected hill station. Both crystalline and bedded rocks abound in joints or divisional planes by which they are separable into blocks, and no small part of nature's work in sculpturing mountains is thus rendered possible. Into these crevices runs the melted snow or rain, and there congeals and again expands, forcing the blocks asunder by slow degrees. The sun's rays turn the ice into water during the day to penetrate still further and again congeal during the night, and this ceaseless process, continued for many centuries, shows its effect in the form of the mountains composed of even the hardest rocks. These are covered with massive boulders quarried by nature's ice wedges in this simple fashion. There, where the dislocation takes place near the edge of a weathered cliff, the mass of ruin caused by the toppling over of huge blocks is often gigantic. Gerard describes the upper portion of Porgyal, Leo Porgyul, as the wreck of some towering peak burst asunder by severe frost. Fraser tells us that the summits near Gangotri and Jamnotri are a mere confused mass of huge crumbling boulders, and the same description applies to nearly all the peaks that have been visited by travelers. Avalanches. We have next to notice snow in the form of avalanches as one of the tools employed in mountain sculpture. The winter snow, when exposed to the summer sun and influenced also by the heat of the earth itself, is often detached in masses sufficient to cause great natural disturbances. It has been suggested that the change in the bed of the Sutlej in the plains to its present one has been produced by an avalanche in its upper course having dammed up the river. In time, the barrier gave way and sent down an immense flood to the plains, sufficient to carve out a more direct course which the river itself has since continued to occupy. It is, however, to the action of snow in the form of glaciers that the more important results are due. These great engines of denudation have the form of a solid river ever progressing downwards through the valleys until the point is reached where the rate of motion is balanced by the melting of the ice. In the figure of the Pindari Glacier, given hereafter, it will be seen that the glacier fills the bed of the upper valley and is fed by the drainage of the snow covered slopes on either side. Its face is discolored with mud and stones and is utterly unlike one's preconceived idea of masses of ice. Along the sides and edges, too, are rows of earth, stones, and boulders transported and deposited in order by the ice stream. These deposits are called moraines. Much of the material transported falls down into the crevices and gets between the bottom of the glacier and the rocky bed along which it moves, and which is thus subjected to a grinding process that reduces even the hardest rocks to powder. This fact accounts for the turbid character of glacier streams, especially near their source. The influence of glaciers, therefore, is twofold. Firstly, in transmuting materials, and secondly, in reducing them to mud or sand. The combined result is often seen in the mass of detritus heaped up towards the end of a glacier called a terminal moraine, and in the striated and smoothed appearance of the rocks that have been subjected to glacial action. As will be seen hereafter, there is sufficient evidence of a great extension of glacial action in former times that must have had a very important influence on the form of the mountains. Cunningham records three great inundations of the Indus due to the bursting of glaciers in the upper portions of its course. These had dammed up the riverbed and eventually gave way, sending a flood down the channel, which in the cataclysm of June 1841 appeared as a wall of water some 30 feet high, destroying everything that came within its reach. Rain. Rain has had even a more constant and penetrating influence on the mountain masses than any of the preceding forms, for it has furnished the materials from which the ice has been formed and is more universal in its operations. The salts and acids contained in it have also had a peculiar action of their own. Rain, while falling through the air, takes up some portion of carbonic acid, and when it reaches a rock, dissolves and carries away certain portions of its texture. The result of this process is that not only is the rock reduced in bulk by chemical action, but what remains also becomes more easily operated on by the mechanical action of falling water in the next shower. For illustrations of these processes, take any line along the limestone ridges about the hill sanitaria already mentioned, and it will be seen how the outer crust where exposed is crumbly to the touch and has a rough sandy appearance. For those who have seen the long gneissic range extending from Almora to Devidura in Kumaon, there could not be a better example of the influence of rain or rock than is there exhibited. Along the road on each side where the rock has been exposed to the weather, the outer layer is removable by the hand, and at the base will be found a little heap of sand that has been weathered away in course of time. Many of the more loosely formed shales, especially those that contain alum, speedily decompose on exposure to the atmosphere, and it is on this account that in the midst of rocky formations in the Himalaya, it is so often very difficult to obtain good building stone. Another familiar example of the influence of the rainfall on the rocks will be seen in the stones of old buildings throughout the hills. Where protected from the weather, their surface exhibits the faintest trace of the graver's tool intact, but where exposed, they are worn and eaten into, and the outer skin appears granulated and rough. This waste of rock material has been in progress for centuries and has produced a soil in which trees have taken root and shed their leaves to produce by decomposition and mixture with the waste The rich vegetable mold that overlies our forest clad hills. The presence of these trees has had the further effect of retarding the removal of the newly formed soil not only by absorbing a portion of the chemical elements carried down by the rainwater, but also by breaking the force with which the rain would otherwise fall on the soft soil. Thus, we find that on well wooded hills, the depth of useful soil is considerable and that springs are numerous and abundant. On the other hand, where the hills have been cleared of forests, the finer soils are soon washed away by the almost tropical rain. The rocks from which the soil has been formed again appear at the surface, and the rainfall rapidly drains off, leaving no supply for springs. And if the process be continued over any considerable area, cultivation becomes impossible and the climate is essentially altered. What deforesting has done for Almora can be seen in its scanty rainfall, its barren slopes, and few springs, although the area affected is so small. Rivers. The action of a river in the sculpture of mountains is threefold. First, it has the chemical action of a rain in dissolving portions of rock constituents. Again, it has in its mountain course the grinding power of the glacier in the force with which it drives the gravel, stones, and boulders along its rocky bed. And thirdly, it has the glacier function of transporting material and laying them down in deposits elsewhere. In the case of glaciers, the denuding process is the more important, and in the case of rivers, the transporting function has perhaps more influence in molding the features of the surrounding country. In the beds of many of our mountain streams, we can detect the action of both glaciers and rivers in the striated and furrowed appearances produced by the former and the rounded forms of worn pebbles due to the influence of flowing water. The muddy color of the water is due to mud or sand held in suspension, and it has been estimated that in this way, 1/6000th part of a foot is annually carried away from the watershed of a great river. This waste is, however, very unequally distributed, being very much greater in slopes and valleys and less in plains. We may be prepared, therefore, with Professor Geeke to find that solely by the continued erosion of running water, even the most recently upheaved mountain chains have had stupendous chasms carved out of their sides and an almost incredible amount of material removed from their surface. Such has been the origin of the Scottish valleys, which, according to the same writer, have been cut out of the general mass of the upraised rock. The existing mountains are what we now find them to be because they have been left standing while the valleys have been excavated among them. Playfair, in his illustrations of the Huttonian theory, as quoted by the same author, writes: if indeed a river consisted of a single stream without branches, running in a straight valley, it might be supposed that some great concussion or some powerful torrent had opened at once the channel by which its waters are conducted to the ocean. But when the usual form of a river is considered, the trunk divided into many branches and then again subdivided into an infinity of smaller ramifications, it becomes strongly impressed upon the mind that all these channels have been cut by the waters themselves, that they have been slowly dug out by the washing and erosion of the land, and that it is by the repeated touches of the same instrument that this curious assemblage of lines has been engraved so deeply on the surface of the globe. In major and minor river systems, the same principle is observed. The lines marking the tributaries of a stream appear like the veins of a leaf, all converging on the midrib, and each forming within its own area a separate main line of a smaller system until the differences are inappreciable. But it may be asked why, if these influences are uniform in their action, the results are so varied. The answer is not far to seek and is to be found in the varied character of the materials on which the aerial forces operate. The southern flank of the Sivaliks below Dehra, consisting of soft sandstones, are weathered by the heavy monsoon rains until they are almost perpendicular. The Kral limestones give their picturesque outline to the outer Himalaya when compared with the other lower ranges. The shales and slates have a character of their own, and the great crystalline range itself owes its form to the rocks of which it is composed. Kamet has its peculiar pyramidal shape from its cap of granite, and Nanda Devi, Trishul, and the Panchchuli have had their peaks defined by simple aerial action on their materials. Thus, our mountain ranges are due in the first place to subterranean disturbances, and in the second place to the action of the different forms of water, chemically and mechanically, on the varied materials of which the rocks are composed. It is the combination of these two forces that gives such varied results, and until more accurate and comprehensive information is recorded regarding their operation, it is impossible to base our physical description on other than arbitrary grounds. Okay, that's the end of chapter 2 at page 110. Thank you guys for those who have followed me till now. We'll catch up in chapter 3 after some time.